Hey guys, Design by Dave here. I just got back from the open sauce show in San Francisco, and wow, what a cool time it was talking to and meeting all these really cool people, talking about building telescopes and astronomy and seeing the cool projects they're working on. I talked quite a bit about my 12-inch telescope, and I realized the video I made didn't include really any technical details or any of the method to the madness, so that's what this video is.
Build stuff!
First thing I want to talk about the design criteria. This telescope is intended for visual use only, as I mentioned in the other video. When it comes to visual astronomy, the Dobsonian style telescope is really king. It offers the best combination of aperture and ergonomics, cost, convenience, that it just pretty much makes the most sense. Just doing a Google image search for Dobsonian telescope, you can see they all share this similar sort of rocker box, alt-az or altitude azimuth style of mount. That's what makes a Dobsonian, is this sort of rocker box mount. It was John Dobson that popularized that. And of course, if you see my channel, it's going to be made using mostly 3D printed parts and carbon fiber. Partially because, well, I have a 3D printer and it's cool, and carbon fiber, it looks cool, and I work with the carbon fiber a lot. But carbon fiber is also a good material for a telescope because it's strong and lightweight and stiff, and doesn't require any additional finishing to, you don't have to paint it or coat it or anything like that. The telescope needs to be disassemblable. I got to be able to take it apart so I can put it in my car, transport it. And I also want it to be a combination push-to and go-to telescope. Sometimes you want to just push the telescope around the sky. It's quick and easy to just push the telescope around to find targets. There's also a certain challenge into manually finding objects, to, as they call it, star hopping, where you forces you to learn the sky and learn to navigate from one star to another to find deep sky objects, faint objects in the night sky. But also, sometimes you just want the computer to do it, or you want the computer to track, particularly when viewing objects with high magnification, like the planets, where they'll drift through the eyepiece very rapidly. So the motion of a push-to telescope is very critical to the user experience. The quality of the optics are really irrelevant if you can't reliably point the telescope at a target, have it stay there, and then adjust and move it to other targets. This brings up the concept of static and kinetic friction. And it turns out, as I was preparing for this video, I did a Google search on the subject, and one of my favorite YouTubers, science educators, Professor Dave, has a great video on this subject. So check the link below, watch this video. We want a lot of friction, because if you had really smooth rolling bearings but almost no friction, when you point the telescope at a target, it would be too easy to bump it, and then it would just slip right away from what you're trying to look at. However, we want the static and kinetic friction values to be as close as possible. So typically you probably understand intuitively that most surfaces will have more static than kinetic friction, right? It takes more force to get the object to begin accelerating than it does to keep it in motion once it's already moving. So the user experience when operating a telescope, that ends up as binding, or as the astronomy community tends to call it, too much stiction. So what happens is you're applying force to the telescope to get it to move. You're trying to get it to move just a little bit. You're pushing, and then it starts to slip, and boom, now you accelerate too fast and you overshoot the target. So then you do the same thing in the opposite direction, and then you overshoot in the opposite direction. So you end up kind of chasing it in the eyepiece. And that makes for a very frustrating experience. And to me, I'm really particular about stuff like that. Some people, maybe it doesn't bother them as much, but me, it really bothers me. That really ruins the experience. So we got to do better than that. The traditional style of Dobsonian telescope uses a combination of this ebony star laminate material and Teflon. This ebony star laminate, or sometimes you see it referred to as Formica, or Formica is a little bit different version of it. I'm not exactly sure. It's basically it's like a plastic sheet that has a texture on, like some kind of texture on one side. You see it in not kitchen counters, but like the backdrop, like the wall of like a commercial kitchen, or I've seen something similar in like a wall paneling in a public bathroom. Maybe you've seen something like that, just to familiarize yourself with the material. And then little blocks of Teflon. And you can see that in this is my friend Dan's 12-inch telescope that he built, traditional style wooden box Dobsonian. And so these are his altitude bearings, and there's the Teflon pads there. A little bit of Dan's video. Check out Dan's video description below. He's got a really nice film on building this telescope. So see here, he's gluing the ebony star laminate to his altitude bearings. So this method works. Obviously, they've been doing it for, 60 years now on traditional style Dobsonian telescopes. It works, but it can have some issues. First of all, it's not mechanically tunable, right? You can't just there's no knob to adjust how much friction. The only way to tune it is to change the size or location of the Teflon pads, or the size of the diameter of these altitude bearings. So that's not something you're going to be able to, just kind of do out in the middle of the desert at night, when you're observing. It also maybe has some limitations on telescope mass. I'm kind of just speculating here, but perhaps it's mostly effective on heavier telescopes where you're going to have more friction overall, because more mass means you have more normal force, and that's directly related to how much friction between the two rubbing surfaces. My guess is that on a lighter weight telescope like I'm building, it's going to be somewhat less effective. It's also potentially susceptible to wear or dirt or grime or getting dirty. So I have a friend who has a very nice telescope that uses this traditional style of motion for the altitude bearing, but it's really bad, and it has just horrible binding, and like I previously described, it just makes it really difficult to get the object centered in the eyepiece when you're trying to move it just a little bit. Very frustrating experience. He doesn't seem to be all that bothered by it, and he brings it out and has great nights of observing. For me, it would totally ruin the experience. I don't know, maybe I'm just too sensitive to those types of things, but yeah, especially if I drove 3 to 5 hours to go to a dark sky site, and that's how my telescope was working, it wouldn't be very great. Also, this method is not particularly drivable. It's difficult to think of how you would add motors to make something like this drivable. Maybe you could do a friction drive type of system. That can work, and I've seen some commercial telescopes that do that. I don't really like that idea. I feel like, again, friction is subject to the surface quality, and if the surfaces get dirty, I can just foresee issues with that. So it doesn't seem like a great solution to me. So the real proper way to do it would be a fluid damped mechanism. If you come from the film or video industry, you no doubt are familiar with the necessity for a quality fluid head tripod for getting smooth, consistent pan tilts. However, a fluid damp system is probably out of the scope for a project like this. Also, I don't really know how those systems work. I have a really nice fluid head on my tripod. I don't exactly want to take it apart and figure out how it works, because I don't want to break it, because I use it, I need it. But also, there's a thick grease in there, and I don't want to make a mess. So one of these days, I will tackle a project like that. Maybe we could 3D print some fluid head mechanisms, and that would be something to look at for the future design on a telescope like this. So my idea is to use gears, partially because we can 3D print gears, particularly these large gears, which would be very impractical, if not impossible, to manufacture with other methods. And definitely, you're not going to find an off-the-shelf gear. This is like a 798 tooth or 794 tooth gear or something like that, or the full 360 degrees would be. So the large altitude gears, on a traditional Dob, you'd call those bearings, but these are clearly gears, so I call them gears. These rest on and roll on these two, the pink here, these roller gears, and they're just held on by gravity. The roller gears are supported with stainless steel shafts and ball bearings, so that gives you consistent rotational motion. And then the shafts engage with these Teflon blocks that are basically like C-clamps. So we can adjust the amount of friction or tension by with a screw adjusting the clamping force around the shaft. So that means we have a mechanically adjustable, on the fly, basically mechanically adjustable damping mechanism, and we have a lot of control because we have it on all four of these rollers. Gears are also drivable, so it solves that problem as well. In practice, it works pretty good. It works damn good, actually, for a first iteration. It could definitely be better, but it's very much usable, and I've had many nights of really fun, enjoyable observing with this telescope, and never had any issues with excessive binding. I'm not sure if I'm ready to claim that it's a superior technique to the more traditional style of altitude bearing motion on a Dobsonian telescope, but I think that it shows promise, especially since it works so good for a first iteration. I would be really interested to see if we could do something great with a really large telescope, how well it would work and be tunable and adjustable on like a big 20-inch, something that's really big and heavy. Would it still be applicable there? I don't know. Maybe it would be. Maybe not. Maybe someday someone will want to build a telescope with me, and we can try that technique. For motion on the azimuth axis, I use this cheap turntable style bearing that I got from AliExpress. It was like $12 or something like that. It's not that great. There's a lot of radial and axial play, a lot of slop in the motion, but for what it is and for cheap, it works pretty decent. A feature I just added last night is this extra little roller here, and this is a gear that meshes with the azimuth gear, and this basically just applies some radial load. So it's sort of like a radial preload to this bearing. And the purpose of that is to take out a lot of slop in this Lazy Susan bearing. That slop was manifesting itself in the form of wobbliness because there's slop in that bearing, so the whole assembly could kind of wiggle like this. So that was making the telescope a bit wobbly, which is one of the main issues I've been having with it. Is it's lightweight and it's a little wobbly, which means the objects wiggle around in the eyepiece. So this extra little block here, this extra little Band-Aid solution actually does seem to help reduce or more quickly dampen out those wobbles. So the whole thing feels a bit more rigid and just all that much better, nicer to use. For damping on this azimuth bearing, I just use these little L blocks of Teflon. Works pretty good, and it's a little bit tunable by adjusting how tightly they're clamped down. Perhaps changing to a similar style of damping as the altitude rollers in this little damping roller here. It could put like a similar Teflon C-clamp on this axis. So perhaps that would be better and more tunable and mechanically consistent with the altitude axis. Maybe that's something in the future I'll look into doing. Next, I want to talk about the go-to system. I didn't feature this at all in the previous video because it wasn't really working at the time. Figuring out a clutch mechanism to be able to engage and disengage the motors has been one of the most mechanically challenging things that I've engaged with telescope design. My solution on here was just as simple as can be, really, is basically just physically move the motors in and out of the gear meshing. The altitude motor is just clamped to this front tube on the base, and by loosening the clamp, I can rotate and slide the motor up and down and in and out of meshing with the altitude gear. The azimuth is quite a bit more difficult. It's connected to the frame with a little piece of linear rail in here, which allows it to slide in and out to engage and disengage the gear mesh. And then there's springs to hold it in tension when it's engaged. So there's springs holding the tension on it. The reason for that is the azimuth gear is not perfectly round because it had to be broken up into multiple parts and bonded together, 5 parts actually, to fit on the print bed. And even if it was printed in one piece, it would likely be out of round by quite a bit. It's also not concentric with the axis of rotation of that Lazy Susan bearing, and there's so much axial radial play in the Lazy Susan bearing, it kind of doesn't matter. It's never going to be, the gear is not going to be concentric with the axis of motion. So as it turns, as it rotates, the gear is effectively getting, the diameter, the radius is effectively getting smaller and larger, right? So by letting the motor and the drive pinion slide in and out, but the spring's holding it in tension, that allows for play. And this system actually works pretty okay. It does kind of still have sort of a, maybe I would say like a beta or alpha feel to it. Could definitely use some refinement, but it's functional. It definitely does work. So basically the springs are always pulling the motor into mesh. So to lock the motor out of mesh, so it's in push-to mode, I have a little thumb screw here that I just drive in. A little bit annoying to have to screw that in, so changing that to like a quick push pin method would maybe be better, or if I had like a toggle clamp or something, would maybe be better. But for now, that system works okay. For the electronics to run it, I'm using OnStep, which is the same software I used on the harmonic drive mount that I built, which is, free, open source, basically fully featured telescope control software, and it's pretty much the only option out there that I'm aware of. I hate to be I hate to be a choosing beggar. Beggars can't be choosers, especially for free software like this. And I'm very grateful for the work that the community has put into it. However, my experience has been a little bit rough around the edges, especially compared to the other open source firmwares like Clipper that I've been using on my 3D printers. Of course, Clipper has a much larger community and much more active development, so of course that experience is going to be better overall. But I guess maybe I'm trying to, and I was talking to a lot of people at the open source show. Maybe I'm trying to like get some software developers really interested in astronomy, and so then they'll try OnStep and go, okay, I can make this better, and then I'll benefit. So, anyways, I don't know. That's a rant on that. OnStep is great for what it is. It works. It's great, but it is buggy. I get random errors, disconnects. The documentation is there, but it can be a little bit lacking or pretty basic. Basically, you have to end up doing a lot of your own trial and error to get things to work right. At least that was my experience. That's been my experience. So that's my short little rant on OnStep. It's great. I'm super glad it exists. I'm not sure if there's any way that I can contribute to the project. I don't have any really coding skills that I can contribute, but maybe just by building telescopes and helping spread awareness, maybe that's a way to contribute. The Shroud was made by my friend Alfredo from GrayFit, grayfitusa.com. He manufactures bags and other soft goods for fitness, sandbags, things used in like CrossFit and other bags. He also makes some hang glider bags and a hang gliding cocoon harness. So if you're looking for fitness equipment, I just want to make sure and give a shout out to my guy Alfredo for that. Check him out, grayfitusa.com. Thanks Alfredo for helping on this project. I redesigned and remade the front ring, the front support ring. The first iteration came out to be quite a bit heavy and too strong. It didn't need to be nearly as strong as it was, which means it was heavier. I saved about 200 grams by basically making the wall thickness a lot thinner and simplifying some of the construction. I also added these slots for the clamping mechanism. So the clamps are basically a print-in-place clamp, and these slots are some stress relief. So that allows the plastic to squeeze down much more effectively, and so it's a much more effective clamp. And it's going to be it's not going to crack or break right here because there's no material there. So that was a good improvement. And I used similar integrated clamping mechanisms in the mirror box for the base of the carbon tubes, the truss tubes, and I did not include those relief clamps, relief slots there for the clamps. So that would be a good improvement on the mirror box if I ever make another one of those. The focuser is also 3D printed. It's a Crayford style focuser. It works really great. There's a few different 3D printed Crayford style focusers on the internet. I basically borrowed design ideas from a couple of them. The key that I found to making this work good is that the shaft is supported with ball bearings. And then I don't have it modeled in here, but there's a Teflon block with basically the radius of the shaft cut into it that is pressing up against the bottom of the shaft. And I can adjust the amount of tension there with a screw in the bottom. And that is the key to getting smooth, damped motion out of the focuser. And that was actually the inspiration for the altitude roller gears as well. Another new feature is the filters and the filter holder. So basically, I made some magnetic filters, so they just magnetically attach to the inside of the focuser draw tube. And that's because I don't really have room to do a filter wheel or a filter drawer like a lot of traditional Dobsonian style telescopes would have. So I can do a kind of the next best thing. It just magnetically attaches to the inside of the draw tube. And that's much better than trying to do screwing filters to the back of the eyepieces in the dark at night. Maybe you drop it, and then you have to change. If you change eyepieces, then you have to unscrew and then screw the filter in. So just being able to quickly attach the filter to the inside of the draw tube is a really great functionality. And because 3D printing is fun and cool, I made these little threaded filter holder cases, so the filters are protected for transport. A little bit about the mirror cell here. The mirror cell is the device that holds the mirror. And somewhat counterintuitively, that's actually a pretty big engineering challenge, is how you hold the mirror. Because it's very sensitive, and if you're holding it too tight or putting too much pressure in one place or another, you can cause it to distort the mirror shape, and that can result in distorted images. So as we say, pinched optics. For some knowledge on that, check out Lockwood Custom Optics. I'll put the link in the description. They have a couple of great articles on design of mirror cells and their experience building really large. And these are like mirror cells for like 30-inch mirrors. So basically, if you follow their design guidance for a 30-inch mirror, it's going to work fine for a 12-inch mirror. So I use a sheet of carbon fiber, 2mm carbon fiber, and then with this 3D printed backbone, and that's bonded on with structural adhesive. And then I have it's what we call a 6-point cell. So these red dots here are what actually physically touch the backside of the mirror. And then those are mounted on these seesaws. And those are supported with ball bearings, so those can rotate freely. And then these on the edge support is what they refer to as a wiffle tree design. So these are also mounted on bearings so they can rotate. And then the actual parts that touch the mirror are bearings, so those can rotate also. So basically you want to hold the mirror kind of as unconstrained as possible. But for more details on that, check out Lockwood Custom Optics articles. They're really great. The total weight, I finally weighed the thing. People keep asking me, and I was curious too. I weighed it, the OTA, the optics, including the altitude bearings, 30 pounds, and the base, 10 pounds. So the total weight of the telescope, 40 pounds. That's pretty light. I was thinking it was like 50 or something like that, but yeah, 40 pounds. It also kind of works against me because you don't get mass damping. So a really big heavy telescope is naturally going to move smoother and be less susceptible to wobbliness because it's got more mass. Also, this thing is pretty light and gets blown around in the wind. So pluses and minuses. However, I'm really satisfied. The saying is the best telescope is one that you'll use. Because this is lightweight, it's convenient to transport and use. I can just put it out on my balcony to do some observing of the moon or the planets when they're out. So I'm really happy with the weight and how this came out. It's really kind of the perfect telescope for me. Cost was about $2,000 for all the materials to build it. That's pretty good. A commercial off-the-shelf telescope, a similar size, a little bit less than that, not including the go-to drive system. A similarly configured ultralight Dobsonian style telescope from Hubble Optics is about $4,000. So I'm under that, but of course that $2,000 doesn't include my time. I spent a lot of time building this. I have no idea how much. I wish I kept track of those hours. Future development. I really want to proceed on improving and maybe version 2 of this telescope. First thing I want to do is put some effort into refining the gears. I didn't really do a whole lot into figuring out what's the optimal pressure angle and module. Doing some iteration on that to find an optimal pressure angle and module gear that gives smooth, consistent motion. The motion could be a little bit smoother while also being printable. You need something that's going to reproduce on the 3D printer accurately. So that will be the next thing to try. And then from that, if end up finding a different gear profile, would be to remake the gears, particularly the altitude gears and the altitude rollers, and spend some time working on the procedures for getting the seams to work out better. One of my previous videos was on repairing these seams, where I made a mold and ground away the gears at the seam and then recast them for repair. That worked pretty well. Maybe they're like 85% better, but I really want to get to that like 95 or 100%. There's still like a little bit of a tight spot in some of the gears as you're moving it, as it rolls over those seams. So that could be better, and I think I could do better. So maybe the version 2, right? I also want to work on refining the altitude and azimuth damping mechanisms, perhaps changing from these Teflon blocks to a rolled up piece of PTFE or Bowden tubing from a 3D printer, which was put forth by the user Pelf. I think I'm saying that right. And I borrowed that for use on the Davely mount. So maybe we'll try that. That would be nice, because then you could get away from these blocks, which do kind of need, these blocks of Teflon, which do kind of need to be machined, although they're not that difficult to work on. But just getting away from, I want to get away from tools that maybe you don't have. And if we can do everything with a 3D printer, then that would be ideal. Also want to redesign how these blocks, these bearing blocks, connect to the base. I was trying to do too many things at once here, so mechanically this is not a great design. So these blue blocks are basically like C-clamps holding the tubes for the base frame together. And I'm not sure why I did clamps there instead of just like bonding this all. I guess I thought I needed to have it be disassemblable, or I didn't want to commit to gluing it together because I wasn't sure if the whole thing was going to work. But now that I know that does, I could just bond this. So the problem that I have here is, so the screws that are clamping these blocks are threaded into the bottom of these bearing blocks. So as that's clamping down, it's difficult to get these blocks to be parallel, which means the axes of those roller bearings are not parallel and collinear, right? So what I actually have right now is a bit of binding on the in the bearings on these shafts on some of the blocks. So that could be improved, and getting those shafts to be running smooth, so all of our damping can come from the Teflon block. That's the ideal situation. So not quite there yet with the design. That could be improved. That's another future thing to work on. Changing to a different azimuth bearing or finding a way to preload this bearing to remove all of the slop or play in it. I think that's probably not possible. I think having a better bearing system for the azimuth, got to find something better. Maybe there's a similar bearing but better quality. That, of course, is going to be more expensive. But there's still a lot of slop in that bearing, which causes wobbliness. So that could be improved and is something to look into. Refining the balance, so maybe the center point where this altitude rotation is would help. I currently have, I think I have about maybe 5 pounds of counterweight in the back here. So refining the balance so I don't need as much counterweight would be beneficial, or would also allow me to put heavier eyepieces or heavier things at the front end without having even more counterweight. That would be nice, but also removing the weight also means you remove some mass damping, so maybe that's not the best thing. I'm not quite sure about that, but this is why it's on the future. Well, that's why it's on the future list. Increasing the overall stiffness. Structure can still be a little wobbly, so just always looking at ways to increase the stiffness would be great. And the last thing I can think of is just a better, more convenient clutch mechanisms to be able to engage and disengage the drive motors. What I have right now works, but having something that is just all the more convenient will make the user experience better when you're actually using it for some observing sessions. So that's about all I can think of to talk about on this telescope right now. Again, it was a really fun project and continues to be. I'm super pleased with how it works. This is probably like one of my favorite things that I've built. And I was really pleased with the reception that I got at the Open Sauce show. And talking to people really kind of motivated me to think about ways to make it even better. Of course, like all my projects, this is an open source design, designed by Dave.net. I have the SolidWorks and the step files. Feel free to download, take a look, modify, change, whatever. And if you think this is a project you'd like to try to take on yourself, feel free to reach out to me. If you have any questions, comment down below. You can reach out to me on Instagram, wherever. And I'm glad to offer you any guidance that I can. Maybe you don't build the whole thing, but maybe you just take inspiration for this for your own project. I don't know. Thanks for watching the video. I hope you found it interesting. Do hit the subscribe button. I hope to have some more projects coming soon. I'll see you next time.